It's not
Hi everyone.
recording the screen.
I haven't introduced you yet.
No, the screen, no.
First of all, today we have Noel, and he's giving a talk on tidal circularization in close-in gas giant exoplanets. Well, that's what the screen says anyway. So
You're discovering it with us.
lead on.
Right, thanks for coming, guys. I've got some exciting results to show you. But first, let's go through some background very quickly. Most exoplanets have been detected by the radio velocity method. About 400 detections have been made so far, but the second most prolific detection technique is the transit method, which you must have heard a lot about from Ford very recently. And in this case, we've got about 70 examples. And the good thing about these transiting planets is that we can work out their orbital and physical parameters. With radial velocity, for example, you can't work out the actual mass of the planet or the radius, but you can do it for the transiting planets. So I'll take you very quickly through those parameters. The V0 is just the offset in the radial velocity. That's the period. That's the semi-amplitude, which tells you how big those oscillations are, and it's related to the minimum mass, the mass of the star, and the eccentricity as well as the period. That's the eccentricity tells you obviously how elongated the orbit is. That's the argument of periastron here, which is quite interesting in my case because I'm measuring the E and omega. So I'll come back to that. That's the inclination, that's the plane of the sky, that's the observer sitting a few light years that way. And the mid-transit time is over here. It allows you to fix where along your orbit you are, so it's very important to me. And now that we have some 70 transiting exoplanets and we know all these parameters about them, we can switch off from the butterfly collecting and move to some real science. Okay, maybe not. So, knowing their mean densities, we can provide constraints on planet formation models. For example, we can, for example, tell you if it's got a very dense core, or if you look at this plot, which I got originally from Udry et al. 2007, but I've updated it. These here stand out very immediately as having much denser cores than Jupiter, which is here, and that's Saturn there. I'll zoom in on these ones, which represent these are our bloated that you may have heard of. They have densities much lower than Jupiter, although having comparable masses. That's what 12 here. Keep that in mind. I'll come back to it. Tidal dissipation was first suggested by Razio and Ford in 1996. They used it to explain the circularization of an initially elongated orbit by tidal dissipation. And Wynne and Holman in 2005 tried to use tidal heating to explain the hot Jupiter problem, the bloated hot Jupiter problem. Leconte et al. 2010 suggested that tidal dissipation was very important early on in the history of the planet system, but it's not enough to explain the bloatedness today. And currently popular ideas are that there could be undetected companions in the system that keep pumping up the eccentricity, and this eccentricity gets dissipated by tidal dissipation, and that's where the energy is coming from. But Ford et al. Have submitted a paper to Science which suggests instead it's a combination of stellar irradiation combined with tidal dissipation that provides the energy for the bloated hot Jupiters, and not tidal dissipation of eccentricity or eccentric orbits. So the big question for me then is, are these orbits circular or are they eccentric at all? Our present state of knowledge looks like this, but so the blue crosses here represent those planets for which we assume a circular orbit because we don't have enough radial velocity measurements to know whether or not to work out a precise eccentricity for them. These circles are the ones that we know for sure are eccentric, and these clusters are currently believed by the community to be eccentric. And you can obviously see this trend here, which is very misleading, in fact. That's what's 12 there. It was believed to be eccentric at 5%. And it was discovered by Hebb et al. In 2009. They used photometric and spectroscopic data to... Oh, sorry. Right. they use right, the MCMC method that you've probably heard from Ode recently to work out the parameters of the system. And in 2009, in December, Lopez Morales et al. Submitted a paper to the Astrophysical Journal and to archive that suggested that claimed that they had detected the secondary eclipse or the occultation as the planet goes behind the star. Now that places a very strong constraint on the eccentricity because you've got this time delay here. That's the occultation, that's the transit. And for a circular orbit, you would expect it to take half the time to get to halfway across the system, behind it and back in front of it. Whereas for an eccentric orbit, Kepler tells us that the speed changes, and therefore it might take longer or shorter to get there. And this time delay can give you a very strong constraint on the eccentricity. Lopez Morales et al. Claimed that they did detect this delay, and that they worked out the eccentricity to be even larger, at 4 sigma this time. In January 2010 now, Lee et al. Published in Nature, they explained away the bloatedness of WASP-12b. They explained away the bloatedness of WASP-12b using tidal dissipation as their mechanism. However, let's back off from all this for a second. I'll take you through an exciting little simulation. I've taken 12 points at random phases. I've simulated these points using the velocity offset, the semi-amplitude, the eccentricity set to 0, and I've fixed the time of the transit over here. That's in phase. I've spread it out in time, and if I use this data, which for all intents and purposes looks like the data that comes in from the spectroscopy surveys, I ran the MCMC on this and worked out the eccentricity, and it's not 0, it's 0.7%, because in this case I've included the error bars properly. I already have a 2 sigma detection there. I repeated the process and instead added 14 meters per second of noise, but I only account for 5 meters per second of the noise in my calculations. That could happen, for example, if you were to underestimate your error bars on the recorded data. I ran the MCMC on this again, and I got an even bigger eccentricity with smaller error bars, which might remind you of something you saw very recently in these slides. WASP-12b was reported with a similar kind of significance. The 2 lessons that we learn here, therefore, are, firstly, that any noise on radio velocity data added to a circular orbit will give the impression that you're dealing with an eccentric orbit. This is nothing new. Our collaborators in Israel pointed it out to us. There's a paper from '71 by Lucy and Sweeney, which they were looking at binary stars and close-in binaries, and in their cases, they showed that for eccentricities less than 0.1, they were using the reducing chi-squared, whereas we're using MCMC. But the same idea applies. Basically, your estimator is biased, and it gets worse. Because the second lesson that we learn from that plot I showed you is that underestimating the noise will bump up your eccentricity and make your error bars smaller and make you think you have a strong detection. One regrettably popular way of underestimating error bars is this. You might have heard Frederick complaining about it for the last year and a half. And the easiest way to think about this is to just start off with random noise, which should go down as square root 1 over n as you have more points coming in. Consider this, however. That's WASP-12 data from Head et al. And you can see these points here jumping up. I'll zoom in on them. This is just in phase space, but there's 6 of them going on a little trip away from the line, from the test bed. And those 6 points do not reinforce the idea that the orbit itself shifted upward.